This video covers concepts dealing with memory management. Recall that an array list stores items in contiguous memory locations. The ArrayList add method, when called with a single argument, adds the argument object to the end of an array list. The ArrayList add method with two arguments inserts into the list at the index passed in as the first argument the object that is passed in as the second argument. The ArrayList remove method removes an item at the index specified by the argument from a list. When items are inserted or removed from an array list, items must be shifted in order to keep the memory locations contiguous. Let's look at an example of an array list in memory. When an array list is created without a capacity specification, the default capacity is 10. Therefore, elements can be added without the need to increase the capacity of the array list. After the first sequence of statements executes, the array list has 4 elements in it, so its size is 4. To insert an element at the beginning of the array list, all elements must first be shifted to the right to make room for the inserted element. The element is then placed at the specified location. This is a resource-intensive process when dealing with very large arrays. This also holds true for a remove. All elements must be shifted to the left to make up for the element that is removed from a list. A linked list is a linear data structure where each element is a separate object. Elements are not stored in contiguous memory locations, but instead are linked using references to the next object in the list. Each item in the list is known as a list node. Each list node is made up of data and a reference to the next node in the list. A linked list provides a way to efficiently insert or remove items from anywhere in the list. A reference to the first node and the last node in the list are kept. The first node is known as the head and the last node is known as the tail. Let's take a look at what memory might look like for a linked list. The first example shows nodes that are linked together by references. The second example shows how easy it is to insert a 101 after the first node in the list. Notice that the only change is that the reference from the first node has changed to reference the new node, and the new node now references what the first node referenced prior to the insertion. Array lists and linked lists both have their pros and cons. An array list stores memory in contiguous memory locations, and linked lists can store items anywhere in memory. Because an array list is stored contiguously, access to the ith element is quick because an offset can be used to access the ith element. To access an item in a linked list, the list must be traversed from the beginning until the ith element is reached. This can be time-consuming in a large linked list. To insert an item in an array list, elements must be shifted to make room for the new item. If an item is removed, items that appeared after the removed item in the list must be shifted to the left by 1 location. This can be processor intensive when dealing with large lists. To insert or remove an item in a linked list, only the references must be changed. This is quick and efficient. A disadvantage of using a linked list is that it takes up more memory because each item requires a reference to the next item. The region where program instructions are stored is known as the code region. The region where static fields are allocated is called static memory. The name static comes from these variables not changing. Static means not changing. They are allocated once and last for the duration of a program's execution. Their addresses staying the same. In Java, the code and static memory regions are actually integrated into a region of memory called the method area. This method area also stores information for every class type used in the program. The region where a method's local variables are allocated during a method call is known as the stack. A method call adds local variables to the stack and removes them, like adding and removing dishes from a pile, hence the term stack. Because this memory is automatically allocated and deallocated, it is also called automatic memory. The region where the new operator allocates memory for objects is known as the heap. This region is also called free store. Memory is finite, so objects allocated in the heap must eventually be deallocated when no longer needed, which will automatically free up memory locations for reuse. Java handles all memory operations for you using a mechanism known as garbage collection. Garbage collection is taken care of by the Java virtual machine. It is a process that runs in the background that reclaims memory from released objects. The garbage collector will reclaim memory from any object that no longer has a valid reference pointing to it. In order to determine which allocated objects a program is using, the Java virtual machine keeps account of all reference variables referring to an object. This is known as a reference count. If a reference count is 0, then the object is considered unreachable and is eligible for garbage collection. The Java virtual machine marks unreachable objects, and deallocation occurs the next time the Java virtual machine invokes the garbage collector. In this example, we have one circle object that is referenced by two different reference variables. Both circle1 and circle2 refer to the circle object with a radius of 5.2. Therefore, the reference count is 2. When the circle1 object's reference is changed to null, the reference count is decremented to 1. The circle2 object variable is still referencing the circle object. However, when the circle2 object reference is set to null, the circle object with radius of 5.2 has no references. Its reference count is 0. Therefore, the next time the garbage collector runs, the memory will be reclaimed so that it can be reused by something else. A reference variable does not have to be explicitly set to null. The Java virtual machine can automatically infer a null reference once the variable goes out of scope. For example, local reference variables that are declared within a method go out of scope as soon as the method returns. The Java virtual machine decrements the reference counts associated with the objects referred to by any local variables within a method. When they become 0, the memory is deallocated.